without having them all. All right, so going over the quiz, we have apparent magnitude versus absolute magnitude. Which aspect do apparent magnitudes tell you, brightness or luminosity? They tell us brightness. So these two have to do with brightness. And I missed. These two have to do with how much total light is given off the luminosity. So that means for part A, since part A asked us about, or question 1 asked us about brightness, which is brighter as viewed from Earth, so I'm very specific there. Then we just need to say, okay, which apparent magnitude is brighter? And so, I mean, you had a homework problem, which is brighter, a minus 1.5 or a 3.5? I know there's one person who's done it. I wasn't. How do you say that again? Which is brighter, a star that has an apparent visual magnitude of minus 1.5 or plus 3.5? That is one of your homework problems.
The former.
It is the former.
I just don't remember the number.
Minus 1.5.
It's 1.5.
It's the minus 1.5 because it's the smaller of the number. Remember, with the original numberings, 1 were the brightest and 6 were the dimmest. And then they took that and they just expanded it. So if you go, 6 is a bigger number and that's fainter. So smaller numbers are brighter. So 1 was brighter than 6. And what's the next number from 1? 0. After that, minus 1. And so the more negative, the brighter it is. So the sun is something like a minus 25 apparent magnitude star. Because it's really, really bright as viewed from Earth. So the answer there was the one that is the smallest, because that means least positive or most negative for the first one. Now the second question asks us about luminosity. What's the most luminous? So that means the answer is going to be C or D. But we still have the same rule. So it's going to be the least positive or most negative.
I just did that backwards. As in, I separated them correctly, but I did I was on A for the first one and C for the second one.
Oh. Wrong side of the number. Okay, so the keys here were understanding which one has to do with luminosity, which one has to do with brightness, and what means more light, what means less light. The third question then, what evidence do we have of convection on the sun? This was once again a homework question. I relied heavily on the homework for this quiz.
Which I have not done yet.
Who has done the homework? I saw, of course, a hand go up and somebody said D, so I just went straight to that. D, the observation of granules. You'll remember from the video, you remember from the lecture, the granules have hot material coming up and then going back down. So in the center, you have the hot material that's rising up, so they're brighter there because it's hotter. And then it's going down at the edges, it's cooler. And so that's evidence that there is convection. It's direct physical evidence. So we do also have computer modeling, but the computer modeling is not evidence of it. It's telling us from all the physics we understand it should be there. Then the last one, which had the most pieces. Let's start with red giants. What stars do you recognize as red giants in this list? Okay, somebody said Aldebaran. It's a red giant. We had Doobie. That was a correct answer?
Yes.
You're saying yes. Anything else? Okay, so those were the red giants in the list. So you could have gone with either B or D, because I had 2 correct answers there for you to choose from. And then we have to draw ourselves our Big Dipper. So our Big Dipper has something like that. None of us are perfect artists, and I am no exception. And then we have to remember our A, M, A, M, P, M, D. And once you have that, yes, then we have this little one up here is an A. That's too close. That little one is an A as well. And so then we put the names on them. So it's Alkade,
Yes.
Mizar,
Yes.
Alioth,
No.
Megriz,
Yes.
Vector Fed,
Of course.
Marek,
Yes.
and Doobie.
So I got the okay.
And that one up there was Alcor.
Don't they both mean this? Can we just say that they both mean the same thing and they're close enough?
No, we can't. We need to know which was Alkade, which was Alcor. Okay, why did I do this last one? Because last night when we were out there at lab, I went over it at least 3 times. And I want people to be able to do this part, you know. There are other stars to learn. You don't have to learn the ones the Big Dipper. But it's easy to learn them. And I think you can look a little intelligent with your friends when you can point out all of these bright stars that make a nice little asterism. And you can say, no, that's not a constellation. Constellation is an area in the sky. That's the big thing over there. That's an asterism. It's, you know. So that's why I emphasize it. Any questions? Max?
How many points are on this quiz?
It's 20 just like the others.
20 points?
Yeah, it's 5 for each question.
Okay.
So the last one has more pieces, and you don't have. I will allow you to miss a few on the last one to still get full 5. A few. I probably, you know, if you have 2 things wrong, I'll still give you full credit. More than that, I won't.
I just completely forgot to put Alcor. So
I noticed that when I picked it up, but you know what can I do? Hey, you forgot one. It said I did say 8, and so I thought it'd say you only have 7, but yeah. All right, let's get on with the lecture since we've spent 17 minutes. We've talked about the atom, and we talked about the energy states of electrons in the atom and how that gives us a distinctive absorption and emission spectrum. And now we're going to get to some really important things from that emission absorption spectrum. So we've already seen that the emission absorption spectrum tells us about which elements there are. So by looking at the spectrum, because each element has a different set of lines, we can determine, oh, this has this kind of elements in it. Furthermore, we can use the Doppler shift to see how those are shifted to determine how fast it's moving away or toward us. So thank you for taking that away from him, Amelia. Appreciate it.
I get it away. I didn't do it.
Yeah, well, it's true, but I still had to give her credit. Yes, sir. Okay. But now we're going to learn some more interesting things about them. If you remember from the long ago when we did the lab process where we looked at these, you guys remember that? Lab where you shot the photons in, you saw the electrons jump up and so on. The last, apparently he remembers it well. The last portion of that, you calculated how much population you had in the n equals 2 state for different temperatures. Remember that part? Yes, I remember. And what you found was something that looked like this on a logarithmic vertical scale, with a peak that was right here at around 10,000 kelvins. So you have the most electrons in the n equals 2 state if you're at 10,000 kelvins. If it's cooler, you have less. If it's hotter, you have less. What this means is we can look at the relative strength of absorption caused by hydrogen atoms with electrons in the n equals 2 state And the stronger that relative absorption, stronger than compared to absorption from electrons in n equals 3 state or electrons in n equals 1 state, the stronger that relative absorption, the closer it is to 10,000 degrees, or 2,000 kelvins. And so it gives us a way of determining the temperature. And of course, hydrogen, while it is the dominant gas in the atmosphere of a star, it's not the only gas in the atmosphere of the star. And so we do the same thing. We can do the calculations for the population of electrons in different states for different elements as well in the atmosphere of the sun. And then we can take each one and say, okay, we have this much population of hydrogen, which, that would basically just give us two possible temperatures, either here or here. And then we have some other element, let's say it's calcium. And let's say the calcium curve looks something like this. And it turns out that we have, the level here, okay, it'd be here or here. And so for the calcium, we would have those two temperatures possible. For the hydrogen, we'd have these two temperatures possible. And we say, well, from those two gases, I can determine that its temperature must be right here. And so you can determine the temperature really accurately by looking at the relative strengths of the absorption/emission lines in the atmosphere of the star. And so that's actually the method that's used to determine the surface temperature of a star. Now, when I say surface, what does that mean? The photosphere. Every star, like our sun, does not have a surface per se. But we have the photosphere, what looks like it would be a surface from a distance. And so that's where we're calculating the temperatures. So another way that could have been used was Wien's law. But Wien's law actually doesn't give us as accurate of a picture of the temperature. So it's not the way that is officially done. A third method that can be used, which is similar to Wien's law, is using filters and saying, I have this strength in red and this strength in green, and using those relative strengths, which is essentially Wien's law. So there's kind of three ways, but the best way, the way that's used predominantly, is looking at how strong the absorption strengths are. As a rule, because of Wien's law, the higher the temperature, the shorter the wavelength of the peak emission. And we saw that when I brought the lamp out here. When I had it cool, you saw that it looked kind of orangish. And as I heated it up, it got more and more white. And when you looked at the spectra, when it was cool, you didn't even see any blue in the spectrum. And when I heated it up, you started to see the blue, and it became very bright in the blue. Well, that's true of anything that's giving off light because it's hot. And so when we look at stars, we can determine roughly their temperature by their colors. And so last night I pointed out in Orion, if we look at Orion, okay, that's a bad place to draw it because I don't have space. If we look at Orion, I think that's Bellatrix there, but what do I know? Okay, there's my rough picture for Orion. There's more because he's got the stuff out here and he's got the arm up here. But roughly that's Orion. This star right here, Betelgeuse, has a very clear red color to it. This star here, Rigel, has a very clear blue color to it. It's so clear, they're so bright, you can actually tell with your eye that there is a blue tint to Rigel and there's a red tint to Betelgeuse. So based on what we had here, which one is hotter, Betelgeuse or Rigel? Okay, blue is the hotter color because blue is the shorter wavelength, and that's why we have blue, 12,000 K, red, 3,000 K. So you can tell right away that Rigel is a very hot star, whereas Betelgeuse is a cool star. Now, oftentimes the stars aren't bright enough for our eyes to be able to tell, but using a telescope we can still measure the colors. It's just we don't see colors unless it's reasonably bright. Otherwise, we just see black and white. So when we talk about a red giant, you instantly know something about its temperature. If it's a red giant, what does that tell you? It's a relatively cool star. If it's a blue giant, it's a relatively hot star. If it's a white star, it's somewhere in the middle, because white is kind of even mixture of all the colors. So in 1901, Annie Jump Cannon came up with a way of classifying stars based on their color. And so we have this classification, and you really should have this memorized. And this mnemonic is so simple, I memorized it in one try. It's not every good boy deserves fudge. It's O, be a fine gal, or if you're a guy, kiss me. And then they've added two more LT, so like this. So, oh, be a fine gal, kiss me like this. You know, good words to speak to your love. Those are listing the stars in order from hottest to coolest. So O's are the very hottest. O stars have temperatures on the order of 30,000 kelvins. You go on down, B's are around 10,000 Kelvin. A, F, G. Our sun is a G2. What's the temperature of our sun at its photosphere? 5,800 kelvins roughly, so around 6,000. And that makes it a G2. What does the 2 mean? Because you have a pretty big range of temperatures that are in G, they break it up and say, okay, a G0 is going to be the hottest of the Gs. Then G1's a little cooler, G2's a little cooler, down to G9. So we're on the hot edge of the Gs. Now the last two, the L and T, those are newer types, and those are really cool. So the L and T's are really cool. A T may not even be considered a star, it's so cool. It might be just considered a brown dwarf, a failed star. So, oh, be a fine gal, kiss me like this. Well, here's just what I just finished saying. Nothing special here since I said it all. So this picture is showing the spectra of different stars by their colors. And so remember what I told you, how do we determine the temperature of a star? What's the practical method for determining the temperature of a star? Looking at the spectrum, look at the relative strengths of the absorption lines. So if you look here, you'll notice that in the spectra, and I know there's lights on the back, but we're just going to stay like this. In the spectra, there's an absorption line here. Whoops, obliterated it. Excellent. Okay, so there's one that goes from here to here. See that one? It's strongest right there. There's another one that only goes down to there, another one here, another one there, another one there, another one here that goes from there to there. There's one here, goes from there to there. These spectral lines appear at different temperatures. And so what astronomers are doing is they're looking at how much absorption you have for each one of those and taking all of that into account to pinpoint the temperature. And so looking at those lines, you can see that there is a difference in the spectral lines as the temperature changes. And that's how they really determine the temperature. Another thing that you note is down here for the cool stars, that turned out really well. For the cool stars, it's brightest over here in the red. For the hot stars, it's brightest over here in the blue. These are actually, shall we say, normalized in strength because the hot stars are brighter truly in all colors, but the brightest color would be in the blue. The cooler stars are much dimmer in all colors, but their brightest color would be in the red. So I don't expect you to come anywhere close to trying to memorize where the absorption lines are here, but to recognize that the absorption lines are different for each one of these, and that's how they determine what the actual temperature is, and specify if it's an A3, a G2, an M5. So here are the actual data to go with these. So O's are hottest stars. They're around 30,000 or more kelvins in temperature. Super hot. And the features, when you look at the absorption spectra, you see very weak hydrogen absorption lines and ionized helium. Now we have to be clear. A helium neutral atom has 2 electrons. An ionized helium atom could have 1 or 0, but if it had 0, it wouldn't have the absorption. So when it says ionized helium, it means it still has 1 electron. Inside of the sun, how many electrons would the helium have? 0. Inside it would be completely ionized. That was part of what we learned in the song. But in the atmosphere, it's cool enough that it can have electrons. So if you're a very, very hot star, something that its photosphere is around 30,000 kelvins or more, you'll have singly ionized helium and hydrogen in the atmosphere. The absorption spectra, then, if you go down to B, 10,000 to 30,000 kelvins, and you have now neutral helium, so 2 electrons, and stronger hydrogen absorption. Remember, hydrogen absorption is strongest at about 10,000. The A's have really strong hydrogen absorption, 7,500 to 10,000. You get down to F, the hydrogen is weaker, but you start having some metals, especially ionized calcium, giving you absorption. Get cooler still, and you get down to the G's. So the sun here is a G, 5,000 to 6,000 kelvins. The sun is a G2, which means we're closer to 6,000 than we are to 5,000, 5,800 kelvins. And we have weak hydrogen absorption, and we have ionized calcium. Go down to the K's, 3,500 to 3,000. Strong metals. Now we have some compounds, carbon, hydrogen. I don't remember exactly the name for that, which is silly, and CN. Get down even cooler, 2,000 to 3,500. You start having titanium oxide. Cooler, the titanium dioxide disappears, and you have things like water vapor. And then the L's here, really notice the question marks because, like I said, you might not even consider this a star anymore. Strong lines of water methane. So you should have this memorized. You should have the obia, find out, kiss me like this memorized. And you should memorize the temperature ranges that go with them. So spend some time with this table memorizing those 2 things, okay? It's not that often I say to memorize, but it's just important because when you specify star, we say this is, I don't remember offhand anything besides the sun, but it is this type of star and it has this spectral class, or spectral type. So the spectral type is the thing like for the sun, a G2, and that tells you the temperature. So when you know the spectral type, that's the temperature information. So instead of saying it's a star at this temperature, they tell you it's a star that's an O3. And you need to know, O3, well, O's are more than 30,000 Kelvin, so an O3 is in the hot end, so it's well above 30,000. First clicker question. Our sun is a spectral type G2 star. Excuse me, what does this tell us about its temperature? And I'm not asking you for a specific temperature at this point, just is it very hot, mid-level temperature, cold, or extremely cold compared to other stars? Russell, you have yours? Okay, so since he didn't even have it out, I'm going to move on, and you'll get the next one. So we had 10 people who said it's mid-level and one person that said it's extremely cold. Amelia, what'd you say and what was your reasoning? Yeah.
I say it's a mid-level from 3 stars. I went with the acronym for is in the beginning-ish. So it's kind of like middle with acronym, so it must be a mid-level from 3 star.
Okay, so this is our original sequence, and then we have the 2 additional. So that's why I put the separator. And so our sun is a G2, which is middle-ish. Temperatures out here, 30,000. Down here around 2,000 range. And so the sun's somewhere in between. Now, this is not actually a linear scale because this is, 5,800. Anyone with an analytical mind would say, well, going from 2,000 to 5,800 is a smaller change than going 5,800 to 30,000. But we tend to take it as more of a logarithmic and say that's in the middle range. So you could have said this one, and I would have said, okay, right? Because if you use the linear scale, that's absolutely right. If you think of it logarithmically, which is the way we tend to do it, then you'd have this answer. So I'd accept either one. Obviously, for a test question, I try to word it so there's only one that I'll accept. Good answer, Amelia. Okay, next clear question. You got it ready this time, right, Russell? Channel 33. Okay. How do astronomers determine the temperature, that is the spectral class, of a star? This one goes out to the only person who hasn't answered yet. Trying to get his ducks in a row. Got to choose an answer here so I can then have you tell everyone what you chose and why. Go. All right, he's in. And we did not have a clear agreement on this one at all. So, Connor, which one did you choose and tell me your reasoning?
Well, definitely wasn't too sure. As you can tell, I'm the one special person that guessed E, but at the same time, I knew it had to do with when you were talking about the different line patterns, and it's either absorption or emission, but it was like, which one is it?
Okay. So I didn't actually specify if it was absorption or emission, did I? I didn't. So this is a good place for us to clarify that. You have the sun as a mass of incandescent gas, or a mass of, or a miasma of incandescent plasma. The incandescent being the important word for us today. It's giving off light because it's hot. So it's giving off a continuous spectrum of light. And then if you look at the atoms in the atmosphere, because they're close to the source, they're going to be absorbing energy from that. And so what we're going to see is the absorption spectrum because of the way we're viewing it. If we viewed it a different way, we'd get the emission spectrum. It would give us the same information. But because of the way we're observing it, it's the absorption spectrum. So the correct answer here was by comparing the absorption lines. But that's simply from the way we're viewing it. Would Wien's law work? In theory, it would. Let me go back to the pictures that have the information you'd use for Wien's law to illustrate why they don't do it. If you look at this, that doesn't look like one of these smooth curves, right? This is the theoretical Wien's law curve. well, it's actually Planck's equation, but Wien's law tells you where the peak is. So the peak is the peak from this smooth curve. And if you look here, you're like, well, on this one here, I'm not sure where the peak's supposed to be. On this one here, I can tell a little better. This one here, I can tell, reasonably well. But it's kind of hard to pick out where the peak is because you have all of the different absorption lines. And you have different kinds of things causing different kinds of absorption. And so instead of using that, you can get more precise information by looking at the relative strengths of all of these different absorption peaks. Right? So they're looking at all of those peaks and measuring the relative strengths to get the information much more precisely. So Wien's law would work in some cases better than others. For this one here, it would be a pretty dismal failure for the M type. For the G, it would be reasonably good. For the B, it'd be really good. Okay, by looking at its color, the color and Wien's law are essentially the same mechanism. It's just the color is qualitative. That looks bluish, that looks greenish. Whereas Wien's law is quantitative. They're actually measuring where the peak is. So they're fundamentally the same method. And by fitting to the black body curve, that's also the same thing. So those three answers were the same, basically. Okay, binary stars. Can anybody name a binary star?
Proximus.
Not Proxima.
Wait, what's it called? Alpha Centauri.
Alpha Centauri. Alpha Centauri is a binary. A and B, right. Another one would be Mizar. You have Mizar A and you have Mizar B. And Mizar A is a binary, Mizar B is a binary. So what we see is Mizar. With a telescope, you can see it's two separate stars. And then if you use a spectrometer, when you look at the first one, you can see the spectra from two different stars. So what we see as Mizar is how many stars in reality? 4. It's two sets of two, and they're orbiting each other. So they're going around each other like this while they're spinning like that around. It's really cool. And not only that, but Alcor itself is a binary. It's estimated that somewhere around half of the stars that have been observed are binaries. Which, of course, if you think about it carefully, that means probably it's 1 in 3 things you see is a binary. Because, of course, if it's a binary, then that's 2 stars there.
Is there a chance that our stars look like a binary?
Is there a chance? Some people suggest that our star, the sun, is a binary with a companion that is a small dark thing that we haven't observed. Seems kind of far-fetched, but it's
It must be like a black hole that was once another star.
it. Well, no, that it's a. Okay, if we look at Jupiter, if it had 80 times more mass, it would be a star. Right? It's not that far away from being a star. And so Gabby brought this out a week or two ago about a proposal of an additional star with or not star, but planet, I think she said, with a wonky orbit. And it's actually Brown, now I can't remember his first name, who most recently is proposing this because it could help explain some funkiness about the plane of orbits of the planets. But the theory is that maybe there's another massive object, more massive than Jupiter, which puts it somewhere between a really large planet or a really small star, that is a very eccentric orbit with the sun. And so it's just been way far away from us for a long time. We don't have any knowledge about it. There's no actual evidence for it. But it's a theory that might help explain some things. So, are we a binary? We have no evidence to say we are.
Can we even prove it now?
Right now, I don't think we can disprove it. And you can't prove anything. And so it remains an option, but not a likely one. So when you have a binary, everything's going to work the same as it does for a planet orbiting a star. So planets orbit stars, and they don't actually orbit the center of the star. They orbit what we call the barycenter, the center of the mass between the two objects. Well, if we compare the mass of a planet, let's say the Earth, with the mass of the sun, how do those two masses compare?
It's barely, they barely.
The Earth is negligible.
Yeah.
That's why you had that question earlier about why is it that we don't need to know the mass of the planet to determine the mass of the star? Because the mass of the planet is negligible, so we just say the total mass is the mass of the star. But if you have two stars, they're not going to have one as negligible mass compared to the other. And so if you have two stars orbiting in a binary, they're going to actually orbit someplace that's outside of both stars. They're always going to be, one is opposite the barycenter from the other, so they're both going to do circles about the same point, but one with a bigger radius than the other. The one with the bigger radius is the less massive one. The one with the smaller radius is the more massive one. And in fact, we can take the ratio of the two radii, and that would be equal to the ratio of the two masses. So if we can determine where the barycenter is, where the point they're both orbiting around is, which all you have to do is have a little motion, you can determine that. Then, knowing where the center is and how far each one is from that, you can determine the ratio of the masses. Well, of course, using Kepler's law for the average separation between the two, and the period, you can determine what the total mass is. So then you have two equations. One equation that says mass 1 plus mass 2 is equal to, I don't remember the rest of the equation, but it has period squared and semi-major axis cubed in it. And we have a second equation that says R1 over R2 equals M2 over M1. So the more massive one has the smaller radius. And with those two equations, you can pinpoint exactly what the mass of each of them is. Now, this slide, I went over a lot of things that are going to be coming up. This slide specifically is talking about the different types, 2 minutes, the different types of binaries. When I talked about Mizar, I said when you look through a telescope, you can see that there are two stars. We call that a visual binary. It's not visual to the naked eye. It's visual using our optical instruments. So as long as a telescope can differentiate that there are two objects, that's a visual binary. If the telescope can't determine it, then we look at the spectra, and you see the spectra, and I think I have a picture of it. Well, not there. Well, kind of there. If I have two stars going around each other, you're going to have Doppler shifts, and one coming toward you, one going away. So one will have a red shift and one will have a blue shift. But as they go around, they're going to shift. And so the one that was red will become blue, and the one that was blue will become red. And so you can, come on, where's the picture? I don't have a picture for it. I used to have a picture included that just shows, you have spectral lines like this, and I should have used different colors. I'm going to change the color of one of these. Excellent. I'm also going to think clearly. Both of those are necessary. So you have the spectral lines crossing over each other. And of course, you can measure the period just by how long it takes for them to go through the cycle. And so you can say, okay, there's two stars going around each other, and this is the period. And so that's a spectroscopic binary. The last kind of binary, which I do have a picture for, is what's called an eclipsing binary. Eclipsing binary is when one star passes in front of the other. Now, once again, in our physics labs, we did some work with eclipsing objects. If I have two stars and one is hotter than the other, which one gives off more light, the hot one or the cold one? The hot one does. Well, it gives off more light per area. So if the hot one passes between us and the cooler one, are we going to have more light, the same light, or less light than we have if we have both of them visible? We have what? It's actually less light because before we had the light from both stars, now we only have one. But it's the brighter star. If the one that's cooler passes in front, then we're going to have less light than we had if there was the hotter one in front. So you actually have a different dip depending on if it's the hot one in front or the cool one in front. And so looking at the size of the dips, they can determine which one's in front. Looking at the time for the eclipsing, they can determine relative sizes. Just like you saw in lab, if it's an eclipsing binary, they can actually get all of the data and determine the mass information. If it's not eclipsing, they can only determine, well, mass is at least greater than this. And this here is the stuff I already talked about, how they determine the total mass. This was just using solar masses with years and astronomical units. So you did get the total mass from Kepler's law, and then you can determine the ratio of the masses from how far they are from the barycenter. Okay, we're out of time. We have homework that's due tonight, and I'll see all of you on Friday. That is